Hello there. So today we'll be learning about fundamentals of computing weeks 4 and 5. So week 4 is all about digital logic part 2 and week 5 is all about circuits. So digital logics part 2 is mainly we talk about different types of circuits, right? Mainly we learn about combinational circuits. And on the next one we have to learn about sequential circuits. So first things first, we learned what is the difference between these two. Combinational circuits has no memory, whereas sequential circuits has memory. So this one only has present input, whereas this one has present and past input. Okay, so today we will be learning about all of them. So buckle up because today is a bit of a complicated roadshow. So the first circuit we are going to be learning about is known as a half adder, right? So the half adder is essentially so today we'll be starting off with the half adder. Well, what is a half adder? Well, the half adder is used to add single bit binary numbers. So you can only add two numbers here. So two binary numbers. So let's say you have A and B. What are the combinations that you can have? So you can have 0, 0, 0, 1, 1, 0, and 1, 1. If you add 0 and 0, you get a 0. If you add 0 and 1, you get a 1. 1 and 0, still a 1. But if you add 1 and 1, you're supposed to get a 10. How can you make a logic gate circuit to do this, right? To carry a 1 over? Well, you do it with two parts. So you have an A and you have a B. So the A can come over like this and B goes over like this. Then you connect these guys to a exclusive OR gate, right? And then you connect this to an AND. Sorry about my bad drawing, but this will be your sum and this output will be your carry. So I believe when you look at this, you should be able to visualize this, but let me explain. So when you have a 0 and 0, you're going to get a 0 here, right? When you have a 1 and 1, you're going to get a 0 here, but you'll get a 1 here. Any 1 and 0, you will get a 1 here. So it essentially acts as a singular adder, right? So this is how the circuit works. So we can only form three outputs out of this. We can get either a 0 or a 1 or a 10, right? Right. So I want you to remember that this is a carry, okay? This is a carry. It carries over a 1 to the other side. The next one we have is known as a full adder, which surprisingly consists of two half adders. How does it work? Well, this full adder, the difference between full adder and a half adder is that it can be used to add multiple bits, right? So what's the point of adding multiple bits? Well, this is how you do addition, right? So what you're looking at is one tiny component of the entire additional process, whereas each adder represents one column. Okay, so let's say you have 1 1 0 1 1 and 1 0 0 1 1. Each half adder or full adder represents the addition that is happening over in one column. Remember that and everything will be easy. Okay, so a full adder is made up of two half adders. How is that? Well, first let us draw one half adder. Exclusive OR gate and AND gate. Okay, right. Then you have a third input. Both of these go into a half adder and they make an output, and this guy, this sums one, some line connects over with the other guy to make another AND gate. Okay, and the previous AND gate, all it does is it connects with this AND gate to make with an OR gate, right? So here's your new sum and here's your new carry, right? So remember these are connected. So if this is A, B, this is also A, B, but this is a new one, C. What is this C? This C is the carry from the previous bit, from the previous adder. So the previous adder can be a full adder or a half adder. It doesn't matter because only in the first one are you going to get maximum of 3 outputs. You can have, so let me explain this to you in a bit of a better fashion. Okay, now let me explain this to you in a way that you may understand. So let's say I have the numbers 1, 1, 1, 0, 1, 0, 1, and I'm adding 1,000 to it, right? So in the very first column, you can only have 4 different variations. You can only have a 1, 1, 1, 0, 0, 1, or a 0, 0, right? So the maximum you can get from that is a 10, where 1 gets carried over. But after that, the second to nth column, you can also get this, right? You can have a 1, 1 and a 1 carried over from the other side. How are we going to deal with this one? So that's what I'd like to say. First off, there's a half adder to take care of the first leftmost column, sorry, rightmost column. And then every other adder is a full adder, where the C is the carry from the previous adder, right? So if you look at the, if I would like to redraw the, so if we redraw the circuit, forgive me for my very ugly drawing. I'm trying my best here, guys. Along with that, now we have a C. So the C goes over here, makes an O exclusive OR gate here. Connect with this to make an AND gate. This line and this line makes an OR gate, right? So here's what happens. Let's say you have a new A and B. It's a new column. Okay, this is a very bad example. Let's add 2 more, right? So the first half adder adds a 1 and 0 gets a 1, no issue. So a 0 is moved over here, right? Carried over here. So 0, 3 zeros make up a 0. Another 0 gets carried over here. So 1 plus 1, 0 plus 1 plus 0 is 1. Same happens here. Let's look at this. A 0 is getting carried over here. So 1 plus 1 makes a 0, but there's a 1 over here now. Now look at this. When this 1 gets carried over, this works as a half adder. So the first two values, the one that are in the addition line, 1 and 1. So a 0 is over here in the sum and 1 gets carried over, right? So this C has a 1 as well, right? So what it does is it sends the 1 to the exclusive OR gate, the new exclusive OR gate, and remember, since the 1 gets carried over and this is a 0 for over here, this makes a 1 and 0, right? Which gives an output of 1 because it's different. Whereas this one and the other one, okay, so this 0 connects to this one, and AND gates don't like a 0, so here's where I get a 0. But remember, this 1 is carried over here through this B gate, which will add up with this OR gate and make an 11. So I believe I didn't explain it so well, but why don't you, the best way to know, look at this is to draw the circuit and try out each and every single value, every single values of how they work, so you can get a visual representation of how shit works. So this is full adder and half adder. Next, we have binary multiplication. So when it comes to binary multiplications, we learned in mathematics for computing. You simply multiply just like any other number. But when it comes to computers, they have a specific process. So they do it exactly as we do, but with a little tiny twist that makes much more sense to you. So here's what happens. First, there is the number. Let's take a 7 into 50. Okay. So when it comes to binary multiplication, we know we have to convert these decimal numbers into binary. So 7 is 111, and I believe 15 is 1110. So if you multiply these two numbers in normal multiplication form, you simply multiply them, you rewrite the value with a small shift. So here there's a 0 and here there are two zeros. So the number is shifted, right? A bit. So how you have to explain this is a bit different from the usual way. So you just have to give the process a little bit of a buff. So what you want to do is you want to take the smaller value. I want to break it into chunks, small chunks, each number. So I'm going to put 111 as A, B, C. So first off, I take the bigger number, 1110. All I do is I multiply it by A first, or C, whatever you fancy. So we multiply it by, actually we have to multiply it by C because if you multiply in this direction. So I take C first and then we multiply it. So we're going to get 1110, right? And then what we're going to do is we're going to shift it a bit. So we're going to get 1110. We add another 0, right? And then we again multiply it by B. And then we repeat the process until the final thing and we add it. So we get the addition, we multiply, and then what we do is we add them. So it's basically, don't put your mind too much about it. It's simply normal multiplication with just shifters, right? Instead of you just simply writing the numbers, you're gonna add a 0. But the why you need to know this here is simple, because you need to know the function of something called a shifter. So there are two shifters, obviously. You have a left shifter and you have a right shifter. So essentially how it works is, let's say you have a 8-bit shifter that starts from D0 to D7, output is S0 to S7. And then there is C, where if you get 1, you shift to the right, and if there is a 0, you gotta shift to the left, right? So there is a diagram out there where you can beautifully see it, where how everything happens. Uh, Remember, it's not, you don't have to know the entire diagram, but you should know what a shifter does and how it works, right? So I highly recommend you guys go check it out. Go take a picture of. Uh, in fact, I believe it would be best if I show you myself. Okay, so here is the image of shifter. Now this D, now they have renamed it a bit, so I'll not rename it. So this is gonna be C. This is D0, D1, D2, D3, and so on and so forth. So let's say we have a number that is 1, 1, 0, 1, 1, 0, 1, 0. So to do the math, we have to shift it 1 to the left, right? So to the left, so we keep C as 0. So if C is 0, this line becomes 1 and this line emits a 0. So if this is a 1, right, what happens is this one does not get anything, right? So this gets a 0. So this is 0 from here. This one travels along here, right? And it sends a 1 over here. And D1 comes over here with another 1 that gives 1 over here, right? So then we have the one that travels through like this. It travels here, it gives a 1 here. This 0 comes over here, that is sent over here, and 0. So I believe I have made a mistake, as in like I forgot, like maybe if it gets shifted over here, unless there's an output, this one is going to get cut. But so on and so forth will happen, and it's best that you know that this is actually a shifter. That's all you need to know. So next up, we'll talk about comparators. Comparators are used to check, if two things are equal. So let's say we have cat that is A and we have cat that is B. You want to check if they are equal, the same, right? So how does this work? Well, for each bit, we have a exclusive OR gate which connects to a NOR gate. So why an exclusive OR gate and why this? Why this pattern? Why not use AND gates? Well, here is the thing. If you have the same values, right? So as you know, this gives a 0, this gives 0, this gives 1 and 1. So if you have the same values, right, you get a 0. And if you get only all of them as zeros, you're going to get a 1 over here. Let's say you get even at least 1 here to this OR gate, which will convert into a 0, right? So if there is at least one difference, right, there's a 1 over here which will be added here, which when it comes over here will become a 0. That is how a comparator works. So comparator is made up of exclusive OR gates, and all of them are connected to a NOR gate, right? That is how a comparator works. So next up, we have something called a decoder. So there are some rules about decoder. If there are n number of inputs, okay, there are n number of inputs, then there will be 2 to the power n number of outputs, where m, if m is the number of outputs, it should be less than or equal to 2 to the power n. So there can't be more than 2 to the power n outputs if there are only n inputs, right? So why is that? Well, essentially, what a decoder does is it takes specific binary inputs and activates one output, right? Let's say we take A, B, So we have 0, 0, 0, 1, 1, 0, 1, 1, right? So we have two inputs. That means we have 2 to the power n, which is 2 to the power 2, which is equal to 4 outputs, right? So here we will have F0, F1, F2, F3. F0 will only activate when A and B are both 0. AB will only activate when one of them is 1, so on and so forth. So this is what a decoder is essentially, right? So how do you draw a decoder? Well, if you use your brain a little bit, I don't mean to offend anyone who doesn't have one, but I think it's a bit simple. So first up we have the inputs, right? Let's draw A and B. Next up we have our AND gates, because obviously we need very specific outcomes. Then we have two ways of getting an answer. So F0 needs both of them as 0, right? As you remember. So we'll connect this and we'll connect this. Let me use a new color for F1. F1 is, remember, A is 0, B is 1. So what I do is connect this and I connect this. Now let me pick another color for F2. F2, remember, B is 0 and A is 1. So I'll connect this. So connect this. And finally, F3 is when A and B are both 1. So I do this and I can do this. Remember, you must do it a bit more beautifully, but this is how a decoder essentially can be drawn using truth tables. So this is a 2-bit decoder, right? And it's also written 2 to 4 decoder. How are you going to make a 3 to 8 decoder? Well, 3 to 8 decoders are made using two 2 to 4 decoders. Isn't this concept a bit familiar? Before, to make a full adder, we used two half adders. Similarly, to make a 3 by 8, 3 input and 8 output, we use two 2 by 4. How does that work? Well, here's how. Minute. Right. So let's say we have A, B, and C. So we have one 2 to 4 decoder and another 2 to 4 decoder, right? So one will have 4 outputs, another will also have 4 outputs, right? So this goes from F0, F1, this starts at F4 and ends at F7, right? So essentially, we're going to connect A here, we're going to connect B here. We'll also connect A here, we'll also connect B here. We can also connect C to here. So the first one, when it's 0, so it will activate, but when it's 1, this will activate. So my drawing is a bit bad, I know, but please try to understand the concept. It's not about the drawing, right? So this is how a 3 to 8 decoder works. Okay. So we learned about decoders, right? Now let us learn about an encoder. An encoder takes an 8 input and converts it into 3. Takes a 4 input and converts it into 2. Well, this is a simple AND gate structure. I think you can understand, right? By saying this activates, so activate this. So encoder is actually the opposite of a decoder. Next we have a multiplexer. A multiplexer has, say, n number of let's say it has n as a value. So it will have 2 to the power n number of inputs, n number of they say selection input, and one output. So if I take a multiplexer that has two selection inputs, then we'll have four inputs and one output, where we can select using these values which one of these will go through, right? So what I can do is have four inputs like this, and using S0 and S1, I can select which one of these inputs will activate. So that is what a multiplexer is. And to draw a multiplexer, we use simply AND gates. So to describe the same exact scenario, I have four AND gates, which will all connect to an OR gate. So how does the AND gates work? Well, you have S0, S1, I1, I2, I3, I4. So this one connects to this one connects to this one connects to this one connects to this. So remember, I1 activates when both of these are 0. So again, we can make a no system and an yes system. So this will go over here, and so will this. I2 activates when S0 is 0 and S1 is 1. So what I can do is I can connect this and this. I3 activates when S1 is 0 and SO is 1. So I can connect this and connect this. Whereas I4 activates when both of them are 1. So when connecting all of this, this is how a multiplexer works. Next, we have something called a PLA, Programmable Logic Arrays. So it is a general chip with so many circuits inside. What we do is we blow out some chips and make a specified chip that is made for a specific purpose or a specific function, right? A PLA has an array of AND gates and OR gates, and some of the AND gates have NOT gates, right? So an ALU is an arithmetic logical unit that can do AND or OR operations, and it can also do sum operations using the half adder and full adder below. So each ALU has one of these, right? And a computer has many ALUs connected to one another infinitely. Not infinitely, a lot of them are connected together so that they can all do functions. So this is data logic 1, that is week 4. Now let's move on to week 5, where we learn about sequential circuits. So we have something known as latches, right? So latches is like a memory. So it has only two inputs, and we have two types of latches, the SR latch and the D latch. So SR latch has two latches, S and R, and D latch also has one input. So let's see how they work. So an SR latch, S stands for set and R stands for reset. So both of them go through an no a no gate, right? So it goes like this, connects to here, right? This is gonna give us a Q, and this is gonna give us a Q dash. So the table is like this. We have S and R, 0 0 0 1 1 0 1 1. So when you have a 1, so 0 0 is actually meaning keep state. We only consider Q here, by the way. Keep state. So when you have a 0 and 1, what happens is you get a 0. When you have a 0 and 1 again here, you get a 1. Whereas if you have 1 1, that's an invalid input. Again, I would recommend you guys go check up on latches, do your own research and all that stuff. So a D latch replaces an SR latch with a 1 latch that has a 0 and 1, right? So if you put a 1 here, it'll go 1 here, it'll come 0 here, so on and so forth. That is an SR latch and a D latch. Okay. All right. Next, we have something known as a clock, right? So a clock circuit emits pulses which are precise, right? So we can use clocks to make flip-flops, right? So we can have one specific signal like this from a clock, and we can phase shift it using a delay so that we can get the respective time that we want. So this can be used to synchronize many of the computer's inner parts, especially the logic parts. So there are two types of flip-flops. Let's say again the same flip-flops, SR flip-flop and D flip-flop. And the only difference is we simply add a clock. So as you remember, the SR flip-flop goes like this, right? And then we have R and S, right? So the clock that comes over here makes an AND gate with this input, right? A D flip-flop is also the same thing. There's a clock which activates specifically with each part. So it's the same thing, right? So all the difference is it'll activate with specific clock parts only, right? So along with that, we have something called registers. Registers, we learned this in the first few weeks. Registers you are used to store data, right? And registers are mainly made out of flip-flops. Okay, so what this is essentially tiny registers are all made up of different types of flip-flops, all connected to each other, right? So this is all there is about week 4 and week 5. I hope you understood. Have a great day.